Hello, this will be a tutorial for the SERS simulator on NanoHub. I will divide the tutorial into parts, so look in the description for where each of these parts begin. The first thing we need to do is open up our web browser and go to NanoHub. Once we're there, just click on the search button and search for the SERS simulator tool. It should be the first result that pops up. Note that you'll need a NanoHub account and be logged in order to use the tool. So once we're on the tool page, you can just go ahead and launch the tool. In this part of the tutorial, I'll talk about how we input our desired molecule into the simulator using the molecule input tab. The default values for the data are for pyridine, and it also includes the A tensors and the C tensors that are needed for field gradient contributions. It is important that we know the orientation of our molecule within the coordinate system used to calculate these polarizability tensors. And for the pyridine molecule here in the default data tab, it's for pyridine in the YZ plane as shown here, with the nitrogen pointing towards the negative Z axis. Now, the molecule's data has to be particularly formatted, and the format is as follows. We specify a new mode by using the mode keyword followed by the frequency of the mode in wave numbers. This tells the simulator that the next three lines are the polarizability of the molecule, formatted as such. This is the XX, XY, and XZ components, the YX, YY, YZ component, and so on. And if we need the field gradient contributions, we also need the A tensor and the C tensor. And so the A tensor keyword will tell it the simulator that the next three lines are the A tensor polarizabilities, as formatted as follows, where the rows here are the dipole parts of the A tensor, the X, Y, and Z contributions, and the columns represent the quadrupole contributions, the XX, XY, XZ, YY, YZ, and ZZ contributions to the A tensor. And similarly for the C tensors, both the rows and the columns are the the quadrupole contributions, the XX, XY, XZ, YY, YZ, and ZZ contributions respectively. Note that the information here does not accept empty lines. And then we just specify the second mode to tell it that the data following that line contains information for this mode, for example. Now, if we would like to input our own molecule into the simulator, we need to first delete this or upload the formatted data from some file. And so we're going to do that for water. And we're going to use this data here for water molecule, where these are the polarizability tensor for the three modes in water. And just for anyone that's curious, this is the orientation of the water molecule within this reference frame, where the water molecule is again in the YZ plane with the oxygen pointing towards the positive Z axis and the hydrogens pointing towards the negative Z axis. So we could either go ahead and delete this information and type in the information for the water molecule, or we could just upload a text file with this data already formatted. So we're going to go ahead and upload that data here by just searching for it, and there they are, water polarizability. Just click upload, and there we go, the data for the water molecule is uploaded. The graph tab controls the output spectrum, and the options are pretty much straightforward. We assume that we're broadening our spectrum using a Lorentzian, and so the FWHM describes the full width at half maxima of the Lorentzian used to broaden our spectrum, and it's set to a default of 10, which I find to be pretty reasonable in most cases. Because we've uploaded a water molecule, we sort of need to readjust our minimum frequency and maximum frequency for our outputted spectrum. So in this case, we'll do 1,000 and 4,000 so that we capture all three of our normal modes. The field tab controls the local fields that are used to perturb our molecule. And that's controlled with this use local field option right here. And so with this option turned off, what we get is the unenhanced or normal Raman spectra of the molecule. By turning this on, we get the surface enhanced Raman spectra or SERS of the molecule. And the model fields that we use to perturb a molecule come from three different nanostructures. There's a sphere, a dimer, and a flat surface. And these three different nanostructures are as follows. For the sphere, we assume that we have some spherical substrate perturbing our molecule, and that's aligned along the z-axis as shown right here. For the dimer system, we assume that we have two identical spherical substrates with our molecule situated in the midpoint between those two. And once again, the z-axis defines the axis of separation between these three different systems. For the flat surface, we assume we have the same system as our sphere system with a spherical substrate and a molecule, but we remove the y and x components of the fields, mimicking what we would get from an infinitely flat surface. And so for these systems, the radius of those spheres are controlled by the sphere radius option here, and the separation for the dimer system is controlled by the separation option right here. Each of these spheres are assumed to be a Drude model, and these are the parameters for the Drude model right here, where the default values are for silver. And so if you want to see what the plasmon from these different structures look like, we could simply go to the output here and look at the plasmon spectrum. And so for the default sphere, this is the plasmon spectrum here, where we find a maximum enhancement around 500 nanometers, and so that's the default. And you could play around with these to get different types of fields. The scattered field option here uses a different enhancement for the scattered frequencies as the incident frequency. And this sort of increases our computational time a little bit, but it also gives more realistic results using more realistic fields. The rotation tab controls the rotation of the molecule with respect to our substrate, our surface. And we use Euler angle rotations around about the x, y, and z axis in the molecule frame. And so 0, 0, 0 just orients the molecule in the orientation that the properties were calculated in. The incident light polarization options describe what polarization of light is perturbing our system. And so polarization along the z-axis, as I've shown before, just polarizes the light along the axis that separates the molecule and the substrate. And we can change these as needed. The orientational averaging option here orientationally averages both the molecule and the substrate together. Whereas the field gradient option here simply turns on and off the field gradient perturbing the molecule. Note that to use this option, we need to make sure that our molecule is defined using an A tensor and a C tensor, as I've described earlier for the molecule tab. And so we could simply use this to change our orientation of a molecule, and that will change the result of our system. And we could check what effect rotating our molecule has on the relative intensities in our SERS system. I hope this tutorial has been useful. In the description below, I'll add the link to the tool on NanoHub, and also links to test cases for molecules, including A tensors and C tensors, and also complex tensors, and how those are formatted in the description. So yep, thanks for watching.